Hi, everybody. It's Miss Nelson. Today is Monday, March 16th, and normally all of you would be filing into my classroom for an earth science lesson, but because of the coronavirus, we are going to have to continue on virtually. I hope you guys are all safe and you are all well at home. So today, normally we'd be starting Unit 8. And we are going to start Unit 8, but of course, because we don't have class as usual, it's going to be a little bit different, but not too bad. So, normally I'd be giving you a notes packet, right? You can still have access to that note packet, and actually, I'll show you where. So, if you go to uh, the Roosevelt High School website, you'll see we have school closed for Monday and Tuesday. But if you click on the Teachers tab and scroll down to find my name, you will come to my page. There's a little bit of information about the regents, and the next part is Remind. So one of the best ways to keep in touch with me is Remind. Most of you have already downloaded it, but if you haven't, now is your chance. You can either download the Remind app on your phone, and then it'll prompt you to put in the code. And I have each period's code listed below. Or you can text the number 81010. You can text the code to that number, 81010. It also says, as of Monday, March 16th, we will be starting Unit 8. And that notes packet is below. So if you scroll down, you can see the Unit 8 note packet. I have also printed out the note packet, enough copies for each student, and that should be distributed at the central office. If not the central office, it is at the school, but I'm pretty sure it's the central office. I will confirm for you soon. So we will be going through the notes and the note packet like we would normally in class. I'm going to be posting the presentations here on my website, and also I'm going to be sending them out on Remind. And then I'm also going to be assigning homework. Now, to start, I only have one homework assignment, and it's going to be due March 20th, and it is a practice regents. So some of the questions you will not know because I haven't taught you astronomy yet, and we are just starting the weather unit, but most of them you should know. So take your time, look through those questions, use your reference table to answer them. But you can click here under current assignments to find it. You just have to log into Castle Learning. I know some of you struggle to log into Castle Learning, but I can always reset your password if you are struggling. The username should be ycsd dot whatever your ID number is, and your password should be your ID number twice, unless you've already reset it. Again, if you don't know your password and you've tried your ID number twice, you've tried what you probably would reset it to, I can go into Castle Learning and change it for you. So that should not be able to stop you. All right, but let's actually get started with our notes. Let me open up my presentation. If you have the note packet in front of you, please take it out, flip to the first page. If you do not have the note packet, I'd recommend that you just take notes on a loose leaf piece of paper. That's going to work out fine too. Regardless, you should be taking notes in some way because studies have shown that if you write it down, you are more likely to remember it. Also, because this is the video, you get the opportunity to pause my lesson whenever you want. So if I'm going too fast for you, pause it, rewatch it. That's the advantage of it being a video. In class, you don't always get to pause me or rewatch something that you don't understand, but here you can. And if you have any questions, please send me a message on Remind. I'll be available. I'm going to keep my phone on me. And I'm going to try to explain to the best of my ability whatever you're confused about. All right, but let's get started. So our first lesson today is our objective is going to be, how does temperature and pressure vary with altitude? For your do now, please write, when you breathe in, what are the elements of air molecules that you are breathing? So I'm going to give you 2 minutes to try to answer this question. Use your reference table, but we're thinking, when we breathe, what air are we breathing in? If you're struggling to find the answer, go ahead, look in your reference table. It is in there. We've already talked about this some point during class. All right, let's see how many of you guys were able to get the answer. So, as I said, we need our reference table to answer this question. So the first question is, what page of our reference table do we need to answer this question? And the answer to that, page 1. Please take out your reference table then and go to page 1. We're going to be looking for the answer to, when you breathe in, what are the elements of air molecules that you're breathing? So we have a couple key words here. Elements in the air we breathe. If we look at the first page of our reference table, down here we have a section that shows us the elements in our crust, hydrosphere, and troposphere. So we need to understand, what is the crust, what is the hydrosphere, and what is the troposphere. The crust, that's going to be the outer layer of the Earth. We learned that back in the dynamic Earth unit. It's that very thin outer layer of our Earth of rock, but that's not the air we breathe. The hydrosphere is water. Hydro means water, and if we look at the elements in the hydrosphere, they're mostly hydrogen and oxygen. It's H2O, that's water. By the way, you can go ahead and label the crust as the outer layer of the Earth, and the hydrosphere is water in your reference table. The last column, though, the troposphere, that's the lowest layer of the atmosphere. This is the air that we breathe. So, what air do we breathe? We need to look down in that column to find out. If we follow those numbers over, we can see the percentage of air by volume and what element makes up that percentage. So 21% of our air is oxygen, 78% is nitrogen, and only 1% is other. And that other can be argon, methane, water vapor, a whole a whole range of things. So now we can answer that question. When you breathe in, what are the elements of air molecules that you're breathing? Actually, most of it is nitrogen. That's 78%, right? We don't normally think about most of our air being nitrogen because our body doesn't really use it. We mostly think of the air around us being oxygen, but that only makes up 20%, 21% of our air. And 1% is other. But our main objective today is to talk about how temperature and pressure vary or change with altitude. So as we go up into the sky, how does temperature and pressure change? In order to answer this question, we need to have a better understanding of what temperature and pressure mean. So for temperature, what is temperature? Most of you, I'm sure, in the morning, most of you, I'm sure, understand a little bit what temperature is. It's how hot or how cold something is, right? But what is temperature on the molecular scale or the really small scale? And temperature is the average kinetic energy of particles. So please go ahead, write down that definition. Temperature is the average kinetic energy of particles. What does that mean? We need to pretend that we took some air molecules from this room and put it in a box. So we now know from our do now that most of that air would be nitrogen. A couple molecules would be oxygen, which I've represented in green, and water vapor is my 1% of other. But if we look at those air molecules, they're not just sitting still. Those air molecules are constantly moving around the room. And how fast they are moving, that is the temperature. So kinetic energy just means energy from motion. And when the air molecules move, the faster they move, that's going to be the higher the temperature. The faster the air molecules move, the higher our temperature. As for air pressure, when the air molecules bump up against different surfaces, they exert a force. So air pressure is the force exerted onto a surface by the weight of air. So believe it or not, those little air molecules have a weight. And when they hit things, when they're moving, they exert a weight. In fact, you are holding up right now 14.7 pounds per square inch of air weight. So if you imagine, hold out your hand, you can draw on your hand a square box. That little box on your hand is going to be holding 14.7 pounds of air. It's actually a weight. We just don't feel that weight because we go through our whole lives carrying the weight of the air above us. So air has mass, and it applies a pressure down on Earth. Because air has mass, it is pulled down to Earth by gravity, just like us. So the same thing that holds us down on Earth, gravity, pulls air molecules down as well. We actually have a lot of information about temperature and pressure on our reference table. So go ahead, flip to page 13 of your reference table, and you'll see that we have information about temperature and pressure. So first, let's look at our two scales. We have temperature and pressure. On the temperature scale, we have the temperatures that water freezes at, room temperature, and water boils. On the pressure scale, we have 1 atmosphere. That is how much pressure is on the surface of our Earth. But we also have different columns for each temperature and pressure. And the different columns each represent a different unit. So for temperature, we can measure temperature in degrees Fahrenheit. We can measure temperature in degrees Celsius and in Kelvin. Pressure we measure either in millibars or inches of mercury. Hg just represents mercury. The advantage of these scales is that it allows us to convert between units. So, for example, if I give you 0 degrees Celsius, you can tell me what that temperature is in degrees Fahrenheit and in Kelvin. So let's do an example. What is 0 degrees Celsius in degrees Fahrenheit and Kelvin? In order to answer that question, I am going to, on my temperature scale, find Celsius, go down to 0, and then I can follow that line over to see what it would be in degrees Fahrenheit and Kelvin. 0 degrees, if I follow that line over, which I've highlighted in green, we can see in Fahrenheit it's between 20 and 40. But what number falls between 20 and 40? Well, exactly halfway, that line that's a little bit longer, that's going to be 30, right? 30 is exactly halfway between 20 and 40. So I'm going to make that line 30. Now, if I count up from 20 to that line, I'll count 5 lines. That means that the Fahrenheit scale is going up by 2s, because between 20 and 30 I only have 5 lines. I got to count by 2s to get there. So that means that this line is 22, 24, 26, 28, 30 degrees Celsius, or degrees Fahrenheit, and now our line in green, 32. That means that 0 degrees Celsius is equal to 32 degrees Fahrenheit. I can do the same thing with Kelvin. So if I follow that 0 degrees Celsius green line over to Kelvin, the green line falls between 270 and 280. Starting at 270, counting up to 280, there are 10 lines. That means each little line represents 1 Kelvin. So that would be 271, 272. Finally, that green line is 273 Kelvin. That means 0 degrees Celsius is equal to 273 Kelvin. So now we can fill out the table. 0 degrees Celsius is 32 degrees Fahrenheit and 273 Kelvin. The pressure scale works in a very similar way. So if I do another example, imagine I give you 1,000 millibars, and you have to tell me what it is in inches of mercury. So we're going to look at our scale, find 1,000 millibars. That's going to be below 1 atmosphere, so less pressure than we feel on the surface of our Earth. And I'm going to follow that line over to see what is in inches of mercury. That blue line falls between 29.50 and 29.60. I know that halfway is going to be 29.55. So each little line is going to represent 0.01. That means that's 29.51, 29.52, and finally our line in blue, 29.53. That means that 1,000 millibars is 29.53 inches of mercury. Now you guys are going to do some practice. So I've given you 5 minutes. Please write down these charts and use your reference table to fill them out. You guys have 30 more seconds, so go ahead and finish up. If you haven't finished, remember you can always pause this video at any time if you need more time, or skip ahead if you don't need all that time. All right, so by now you probably should have filled out this entire table. And so I'm going to give you the opportunity to check your answers. This is what you should have gotten. If you didn't get one of these answers, or you answered it incorrectly, please message me and remind and I can help you out. So go ahead, check your answers. You can pause this video if you want more time to check, but we are going to move on. So now that we know about temperature, we know about pressure, we want to know how temperature and pressure changes with altitude. That information is going to be on our page 13 of our reference table. So turn to page 13 in your reference table and find this chart. It says selected properties of Earth's atmosphere. We're going to take a little time now to look at what information this chart gives us. So the chart is separated into 3 different columns. We have temperature, pressure, and water vapor concentration on the x-axis. On the y, we have altitude, and that is just the height. Altitude just means height. So 0, sea level, you can imagine that line being the ground, and we're going higher and higher up into the air. Altitude is divided into 2 sections, 2 scales, kilometers and miles. In the kilometer scale, we have 0, 40, 80, 120, and 160, and little tick marks in between. If we fill in those tick marks, we can see that we're going up by 10. So you can fill in on your scale, on your reference table, those tick marks, label them 10, 20, 30, 40, 50, 60, 70, 80, all the way up. Miles, though, has a different scale. That goes from 0, 25, 50, 75, and 100. That scale does not go up by 10. If you can try to figure it out, it goes up by 5s. So you can go ahead and label that scale on your reference table if you'd like. Now we're going to talk about each of those different properties, though, in our atmosphere. So the first one is pressure that we're going to talk about. And if we look at the ground, the pressure starts off at 1 atmosphere. And as we go up into the air, the pressure gets smaller and smaller and smaller, closer and closer to 0. This tells us that as we go up, pressure decreases. The reason for that is a similar reason to why everyone flocks to the stage, the same thing that we see during a concert. So in this concert, you can see that everyone is crowded towards the stage, right? Because they want to see the singer or the performer. And the farther away you get from the stage, the more spread out people are. It's the same with air molecules. The closer you get to the ground, the more crowded the air molecules are because they're all being pulled down by gravity. And the farther away you are, the more spread out they are. That means that when you're closer to the ground, you're going to have higher air pressure because, first of all, you have more air molecules that are weighing down on you than when you're farther up. The next column we're going to talk about is water vapor. We have a similar curve for water vapor. So we start off with 40 grams per meter cubed of water vapor at the surface, and then it gets closer and closer to 0. And then it just cuts off. So at about 20 kilometers above the surface, we don't have any more water vapor. And that's important because water vapor forms clouds. And so our clouds are made of water. So above 20 kilometers, we don't have any more clouds. The last property of the atmosphere is arguably the most complicated, and that's temperature. It is also maybe the most important. So the temperature at the surface starts at 15 degrees Celsius. As we go up into the atmosphere, we cross that 0 degrees line. That's freezing. So quickly we drop below freezing, and it goes all the way to negative 55 degrees Celsius. Now that's like negative 70 degrees Fahrenheit. That's really cold. So unimaginably cold. But something strange happens around maybe 12 kilometers, and that's the temperature switches its trend. So first, the temperature is decreasing from 15 degrees to negative 55, but then it starts increasing. So the temperature, as we go further up now, starts getting closer and closer to 0. So we go from so unimaginably cold, freezing, down to just barely freezing. As we go further up, the temperature decreases again. So now we go from 0 degrees Celsius all the way to negative 90 degrees Celsius. That is so freaking cold. Finally, it switches back. The temperature starts increasing again. So we have the temperature going up, the temperature decreases, increases, decreases again, and then increases again. It switches. And that divides up the layers of the atmosphere. So when the temperature is decreasing as we go up, we call that the troposphere. When it increases, that's the stratosphere. When it decreases again, that's the mesosphere. And increases, that's the thermosphere. In each of the layers of the atmosphere, there are important things. So on the notes packet, I have divided them up. There, some of the sections you guys have to take notes on. So we're going to go through each of those atmospheric phenomena, and then eventually you're going to tell me, using that reference table page, what layer of the atmosphere you find those different atmospheric phenomena in. So the first is the ozone layer. The ozone is a gas made of 3 oxygen atoms that protects the Earth from dangerous ultraviolet sunlight. Ultraviolet is UV sunlight. That's the reason we put on sunscreen, because some of the ultraviolet light is able to come through the ozone, but most of it, as we can see in that picture with the umbrella, like the ozone protects us from most of that ultraviolet light, and thus protects us from cancer and all the bad things that UV light can do to us. In fact, like 10 years ago or so, we had ozone depletion, and our ozone layer thinned, and actually there was like a hole due to human activity. That meant that all of that harmful ultraviolet sunlight was able to come through and hit the surface, and it was dangerous because it could give people cancer. But we were able to fix it, so now our ozone layer is strong. The jet stream, those are high-speed winds that influence our daily weather. So if we look at this picture, there's a polar jet stream, that's that blue squiggly line, that goes around the North Pole and carries with it this cold air. The subtropical jet stream is much further south, and it's that red line, and it carries warm air. But jet streams just don't bring cold or warm weather. During World War II, Japan used the jet streams, those streams of air, to drop bombs over the United States. So Japan knew about that subtropical jet stream and used it. They launched bombs on these weather balloons, and the balloons would go up higher and higher into the sky, and one of the balloons would pop. Then the balloons with the bombs would drop back down again, and it would go up further and further, and another would pop until eventually the balloons reached the United States. So here's a map showing where Japan launched those balloons with the bombs on them, how the tropical jet stream brought them over to the United States, and where those fell. This actually didn't cause any deaths in the United States because at the time that area was pretty sparsely populated. Um, so it didn't actually end up being that successful. The next property in the atmosphere are the auroras, or the northern and southern lights. If you're near the North Pole or you're near the South Pole, you can see this beautiful light show. And there's another thing that is in our atmosphere. Also coming through our atmosphere are meteoroids. Those are rocks from space that burn up due to friction with air molecules. Often, we see them in the sky and call them shooting stars, but they're not actually stars at all. They're just rocks falling through our air, and as the air brushes up against the rock, it causes it to get hotter and hotter, eventually to burn up, and that's what we see streaking through our sky. Also going through our sky are weather balloons. Last week we saw a weather balloon carry up burgers and fries into our atmosphere. And so those are those big balloons, and they help us study the properties of our atmosphere because they go pretty far up. So now I'm going to give you another 5 minutes, and you're going to fill out that column that I've highlighted in yellow, telling me about where each of those things that we just talked about, those atmospheric phenomena, what layer of the atmosphere we would find them. So either the troposphere, the stratosphere, the mesosphere, or the thermosphere. Go ahead, you have 5 minutes to fill that out, and I'll check back in with you in another 5 minutes. If you finish early, feel free to skip the video ahead to check your answers. If you need more time, feel free to pause the video. But you now have 4 minutes and 15 seconds to see if you can complete that chart. All right. So let's see how you guys did. We're going to check our answers. So the ozone, which was 20 to 30 kilometers above the surface, that is going to be in the stratosphere. Jet stream is in the stratosphere. Auroras are going to be in the thermosphere. Meteoroids at 70 kilometers are in the mesosphere. Weather balloons at 39 kilometers go to the stratosphere. Airplanes at 11 kilometers are in the troposphere. This one actually, most airplanes go through the troposphere. There are some, like commercial airplanes, that fly in the stratosphere. But most, especially domestic flights, ones that just go within our country, are in the troposphere. And clouds and weather are in the troposphere. So lastly, I have an exit ticket for you. You're going to use your Earth Science reference table, page 13, and the notes that you just took to complete the following chart. This is going to summarize what we learned today about the layers of the atmosphere. So go ahead, write down each of those columns of the chart, or if you have them in the notes, you can just fill them out. We have our troposphere, stratosphere, mesosphere, and thermosphere. You're going to tell me the altitudes, from what to what kilometers do we have that layer. You're going to tell me what happens as altitude increases to temperature and to air pressure, and then finally what atmospheric phenomena that layer of the atmosphere contains. You guys have about 4 minutes to complete this, and then I will share with you the answers. So go ahead, write them down, see if you can complete it to the best of your ability, and I'll check back in another 4 minutes. All right, now's your time to check your answers. So, these are them. Your altitude for your troposphere should be from 0 to 12 kilometers. As altitude increases, temperature decreases in this layer. The same thing is true for air pressure. So as altitude increases, air pressure decreases. And the troposphere contains some airplanes and clouds and weather. And the stratosphere that goes from 12 kilometers to 50 kilometers. This time, as altitude increases, temperature increases. As altitude increases, air pressure decreases. And the stratosphere contains ozone layer, jet stream, and weather balloons. The mesosphere goes from 50 kilometers to 80 kilometers. This time, temperature is decreasing again as we increase altitude. As always, pressure decreases. And this layer, the mesosphere, contains meteoroids. Lastly, we have the thermosphere. That goes from 80 kilometers all the way up to 600 kilometers, which is not even in that chart. It just says it in the little line underneath the thermosphere. As altitude increases, now temperature is increasing again. As always, pressure decreases as we increase altitude. And the thermosphere contains the auroras, those northern and southern lights. So that is our lesson for today. I hope you guys learned about the layers of the atmosphere, temperature, and pressure. I'll be back here tomorrow with another video. Please give me feedback as to how this one went. It's my first time creating an online video, so I'm learning as I go. And I hope you guys stay safe and stay happy. All right. See you tomorrow. Bye.